Okay. Hi, everyone. Um, yeah, welcome to the talk. I'm going to tell you about hypergraph sparsification via chaining. Okay, so let's get laser pointer here. Okay, the setting is that you have a weighted hypergraph. So that's a set of vertices, a set of hyperedges, which are just an arbitrary collection of subsets of the vertices, and then a non-negative weight on the hyperedges. So you have a weighted hypergraph. And what's going to be important to us about the hypergraph is the induced, what we're going to call the energy functional, which is this quantity. So it's a sum over edges with the edge weights present. Again, sum over hyperedges with the edge weight present. And then what we're going to charge for a hyperedge E is the maximum. So, okay, so this thing takes a vector as input. What we're going to charge is the maximum of xu minus xv squared over all pairs u and v in the hyperedge E. So the context for this, or perhaps the right context for this, is that if we just have a graph which corresponds to a hypergraph where all the edges have cardinality 2, then what we would generally be measuring here is the Laplacian quadratic form, which says that basically given a vector x in Rn, it assigns, such a vector assigns a real number to every vertex in the graph. You can embed the vertices according to those numbers. And then for every edge uv, you get a quantity xu minus xv squared, which is which you could think of, for instance, as proportional to the potential energy of a spring that's whose endpoints are fixed at xu and xv. And in this case, for a hypergraph, we're considering this related quantity that you can think of like this. So for a hyperedge TUV, this is now a triple of vertices. What we're charging here is the maximum of xu minus xv squared. So you could think about that, for instance, physically as you wrap a rubber band around all the vertices in the hyperedge, in this case, these three vertices, u, t, and v, and then what you're paying is the potential energy of that rubber band, which in order to stretch around all the vertices in the hyperedge is paying the maximum of xu minus xv squared. You might ask why this is the correct analog for hypergraphs. And there's been a lot of work suggesting that this is the correct definition, like in the setting of diffusion processes on hypergraphs or semi-definite programming relaxations of hypergraph problems. And then this has come up independently in areas like data mining and machine learning. One way to think about that, how it comes up there, is as a regularizer. If you think about the x's as assigning labels to the vertices, then adding this regularizer, which is a convex function of x, basically penalizes labelings that give divergent labels to the members within a single hyperedge. Okay. We're going to talk about sparsification. So the idea is that we want to take this hypergraph H and sparsify it, and we want the sparsifier to preserve this energy. So formally, a weighted hypergraph H tilde is an epsilon spectral sparsifier of H if, first of all, the edge set of H tilde is contained in the edge set, again, the hyperedge set of the original hypergraph, and if the two quadratic forms are multiplicatively close, so close within 1 plus minus epsilon for every input vector. Okay, so this is what it means to be an epsilon spectral sparsifier. And as I mentioned, this arises in a number of domains. And one important difference from the graph case, in the graph case, the densest graph you're going to have is a complete graph with n choose 2 vertices. Here, because the hyperedges are arbitrary subsets of the vertices, the number of edges could be as large as like 2 to the n, where n is the number of vertices. And yet we still want to find a sparsifier where the number of edges in the sparsifier is extremely small. Okay, so in the graph case, you can go from n squared edges maybe down to nearly linear number of edges. Here we're going to be going from possibly exponentially many edges. We still want to get eventually down to something that's near linear. So that's the setting. Okay, so here's my notation. N is the number of vertices. R is what's called the rank of the hypergraph. So it's the maximum cardinality of any hyperedge. And then here's some known results. So I guess as a baseline, one should consider what's known for graphs, which is the case R equals 2. So Spielman and Srivastava showed that in that case, for graphs, one can get the number of edges in the sparsifier down to n log n over epsilon squared for an epsilon sparsifier. I'll mention it later, but of course there's a further work of Batson, Spielman, and Srivastava that gets rid of the log n factor. But we're not going to be close to that regime in this talk. So one can think about this as the gold standard. Can we do this for hypergraph? Okay, so Soma and Yoshida gave some preliminary results in this direction. They showed in 2019 that one can sparsify down to a polynomial number of edges. Remember, this is non-trivial because hypergraph could have exponentially many edges in a number of vertices. Bansal, Svensson, and Trevisan showed that for constant rank R, one can essentially achieve the bound known for graphs. So one can get n log n, order n log n edges in the sparsifier for constant rank. And then in this, it's actually a sequence of 2 works, but I'm just quoting here the last one. I would call a breakthrough. Kapralov, Krothkammer, Tardish, and Yoshida showed that actually one can, for arbitrary rank, get down to n polylog n hyperedges. So something sort of, compared to the graph case, something that's quite close in spirit to the graph case for an arbitrary hypergraph. Okay, so our goal today is to improve this a bit. So here's our main theorem. For every hypergraph, there exists an epsilon spectral sparsifier where the number of edges in the sparsified hypergraph is sort of what one has for, let's say, for graphs in the setting of random sampling, n log n over epsilon squared times an additional log r factor. And so the idea is that this combines sort of the benefits of both of these bounds. So this bound gets n log n for constant r. This bound gets n polylog n for any r, and the bound we're going to give today gives n log n for constant r, and then at most n log n squared for an arbitrary hypergraph. Okay, and I should mention that in this conference, the same conference, Arun Chambalapati, Yang Lu, and Aaron Sidford also have a proof of this theorem. Okay, I'm going to talk about obviously the proof from my manuscript. The 2 proofs are technically closely related, although the presentations are quite a bit different. Okay, so here's the theorem. There exists an epsilon spectral sparsifier where the number of hyperedges is order n log n over epsilon squared times this additional log r factor. Okay, and how are we going to sparsify? We're going to do something that's sometimes called the empirical method. Very simple. Let rho be a probability distribution on the hyperedges. So just what it says. We are going to have to carefully choose a distribution, and then we'll sample hyperedges independently from this distribution. So for some number m, we sample m hyperedges IID from rho, and then we output the hypergraph with this quadratic form. So with the quadratic form, that's the average of all of these rescalings of the sampled edges. So the notation here is that for a single edge, QE of x is just is the corresponding term in the energy. And then the reason for the choice of weights here is the following. It's so that by linearity of expectation, QH tilde is an unbiased estimator of QH for every input vector x. Okay, so like you can see, we sample an edge with probability 1 over rho, with probability rho sub e, but then we weight it by 1 over rho sub e, so that an expectation that a single sample is equal to QH of x. And then we take m samples and take their average. So again, an expectation, we get the correct thing. Okay, that's the idea of the empirical method. And then there's, in some sense, only one thing left to do, which is to analyze how well it worked. So we want to choose capital M large enough. Capital M is the number of edges in the sparsifier such that this expected maximum is small. Okay, so first of all, if you ignore the expectation here and just consider this maximum, if this maximum is bounded by epsilon for every x, where the h energy of x is at most 1, then it's not hard to see that implies that h tilde is an epsilon spectral sparsifier of h. And so, like, if we can prove that the expected value of this quantity is at most epsilon, then in particular, there must exist a choice of h tilde that satisfies this bound. So this is our goal. And again, there's 2 steps here, really. There's first, we want to choose a probability distribution that reflects, in some sense, the geometry of our hypergraph. Note, for instance, this distribution can't be uniform on hyperedges. The classical example in the graph case is if you take two cliques connected by an edge, then in any sparsifier, that edge connecting the cliques has to be included. But if you were doing uniform sampling, you'd have to sample essentially a constant fraction of the edges before you saw that one. And so that would be a bad distribution. And so, you know, this singular edge needs to have a large weight. In fact, it should have probably constant weight in this probability distribution. So the point is the choice of row is extremely important. And then the second thing that's important is having enough concentration that this expected maximum is small, right? Like this is a maximum over infinitely many vectors. So you need some reasonable way to argue about concentration of this unbiased estimator to say that this, you know, that this is the most epsilon for every x, but with QHX less than or equal to 1. Okay, so the first major reduction here is a standard symmetrization argument that allows us to basically get rid of all of the randomness in H tilde and just replace it by some random signs. So I'm not going to go into it now. It's spelled out in the paper. It suffices to analyze for every fixed collection. This should be E1 up to EM, not E1 up to EK. For every fixed collection of M hyperedges, that the expected maximum of this randomly signed sum is at most constant times epsilon. Okay. The idea here is that basically we're trying to show that the influence, like we're trying to argue about concentration in order to bound this quantity. And so at least intuitively, it suffices to bound the maximum contribution that the inclusion or exclusion of a single edge can make to this maximum. And so this is saying, yeah. So if we choose, you can think about these random signs as representing, I mean, it's a global notion of influence, but it's measuring the deviation of this quantity as we vary these signs. And if we can bound that, then by symmetrization, it allows us to get a bound like this as well. Okay, so that's going to be our goal from now on. We want to prove that for any fixed hyperedges E1, again, this should be M, E1 up to EM, that the expected maximum of this randomly signed sum is at most epsilon, where again, these sigma 1, these sigma k's are IID plus minus 1. Okay, so how can you analyze the expected maximum of a random signed sum? Okay, in the most natural way, like first of all, we're taking the maximum over this continuous set of vectors. So let's discretize this set in an efficient way where the number of points in discretization is not too big. And then let's try to say that that this random signed sum, again, like this sum looks complicated, but you know, this is really just a bunch of signs times a bunch of terms. You know, the terms depend on X, that's why things are complicated. But like this sum will tend to be well controlled, like will tend to be concentrated if the contribution from any term is not too big. And in fact, this informs how one should choose these sampling weights so that QEX over rho sub E, it tends to be bounded for most of the edges. Okay, but now our goal is to prove this bound for any fixed set of hyperedges. So let's just have some notation here. V sub x is going to be this random sum. I just dropped off the 1 over m because it's just a scaling. We can add it back at some point later. And then the set of vectors I care about is the set of all x and Rn where the hypergraph energy is at most 1. And then, well, let's say here, what we're ultimately going to be concerned with is the expected maximum over x and t of Vx. This is a random variable. The randomness is all coming from these random signs. And the maximum is over this set T. And then we're going to try to control the expected maximum. And there's a well-known, at least in this setting, there's a well-known theory for doing that, which is called chaining or majorizing measures or generic chaining, which is to somehow bound the expected maximum of this random process in terms of the geometry of the index set T with the metric D that's induced, in this case, by the in this case, D will be induced by basically the standard deviation of Vx minus Vy. So in general, for any sub-Gaussian process, this kind of chaining theory lets you bound this expected maximum. Here's the setting. What is a sub-Gaussian process? It's a process that you can equip with the metric D such that the process has sub-Gaussian tails in that metric. Okay, so like this is the main kind of concentration inequality we want, and it's an exercise to show that when the sigma k's are random signs, then indeed these random variables satisfy this with this metric. Okay, and so what it's going to do is reduce the problem of analyzing this expected maximum to analyzing the geometry of this index set. So this is the set of things with energy at most 1 under this metric D, where the distance is basically the distance between x and y is the standard deviation of Vx minus Vy, absolute value. Okay. So I'm not going to say much about how you choose these weights, except in the next slide. In fact, this was the major innovation of Kapralov, Krothgummer, Tardish, and Nishida. That there's a nice way to choose these importance scores for the edges, for the hyperedges of a hypergraph. The interpretation I'm about to give is from a follow-up work of John Belapati, myself, Younglu, and Aaron Sidford. It's now out in the archive, where we interpret sort of the importance sampling weights from this KKTY paper in the setting of Lewis weights. So we sort of call them block L-infinity Lewis weights, and in that paper we explored a number of generalizations of this notion. But the theorem, the theorem of KKTY restated in this language is that there are weights that you can assign to the hyperedges and some linear transformation from Rn to Rn, such that the sum of the weights squared is n. I should say these are non-negative weights. I guess the square, only the square appears, so it doesn't matter if they're negative or not, but you should take them to be non-negative. And then what happens is basically this bounds the contribution of any single term to the total energy. So this says that, like, if we ignore this intermediate term for a second, this says that WE times QE of x is at most alpha E squared times this energy. Now, of course, this occurs as this energy is a sum of these things over all the hyperedges. So of course, this quantity here is at most 1 times this. Here we're saying it's at most alpha E squared times this. But notice that most of these alpha E squareds are going to be much smaller than 1, because there's a possibly huge number of hyperedges. I mean, in the case when we're trying to sparsify, it's far more than n hyperedges, but the sum of the squares is n. So many of these quantities are much less than 1. And so this says that many of these quantities have a contribution to the energy that's very small. Okay. And there's a second thing that's important here that we'll also need, which is that this inequality is mediated by Euclidean structure. Okay. So like the linear transformation here, you can essentially ignore. You could, if you want to, you could apply Q inverse to X here. The important thing is just that, yeah, so that it's not only that this term is controlled by alpha E squared times the energy, it's actually controlled by this intermediate Euclidean norm. That'll come up soon. We're just going to use this as a black box. In the STOC paper, I give an interpretation of this in terms of just some kind of maximum, I guess, so maybe some kind of maximum volume ellipsoid subject to some constraints. In KKTY, they gave it, the interpretation was in terms of some optimization problem on effective resistances. And I think perhaps the correct interpretation is as some kind of block Lewis weights. And that's the interpretation we give here. We're just going to assume that we have these weights. This is going to give us the rows that we need to sample. In fact, we're going to exactly sample with probability, like we're going to sample E with probability 1 over alpha E squared. Yes, that's correct. Okay. All right. So now we're in this setting where we have these random variables. Remember, these are random signs. So for every x, we have this random sum of terms. And the quantity we care about is the expected maximum over x and t of v sub x. And but this looks complicated. Now I want to abstract out things that, I want to make things more general so they get simpler. So the first thing is to look at this quantity. Let's just recall what this is. This is just some this is a non-negative number times this thing. This QE of x is it's the contribution of this hyperedge to the hypergraph energy, maximum over UV, pairs UV in the hyperedge E of xu minus xv squared. And just note that if you let A be the linear map that maps a vertex to this should be, okay, so there's another problem here that this should be n choose 2, not e choose 2. I want to map a vector into the n choose 2-dimensional vector that has all the pairwise differences. And then if A does that, then this thing here is just if I restrict my attention only to pairs that where u and v are both in the hyperedge E, and then take the infinity norm and square it, I just get this quantity back. So the point is that this quantity here is some non-negative number times basically times the square of a norm. And it's not the square of a norm because this is because we restrict to a subset of the coordinates, this might only be a semi-norm. But that's going to give us the first step of our generalization. Instead of analyzing, something that looks complicated like this in the hypergraph setting, we're just going to analyze random sign sums of squares of semi-norms. And a semi-norm on Rn is exactly the same as a norm. It satisfies these first two properties of a norm. The only property it may not satisfy is that non-zero vectors could have norm 0. And in fact, it's not hard to see that basically a semi-norm on Rn can, you can decompose Rn into a direct sum of two pieces, such that on one piece the semi-norm is 0, and on the other piece it's a genuine norm. So there's, semi-norms and norms are. A semi-norm is just a norm on a subspace and then 0 on the orthogonal complement. Okay, so like this is already one simplification. We're just going to consider randomly signed sums of the squares of norms for arbitrary norms. And then again, we have this set T where, containing all the vectors where the hypergraph energy is at most 1. So yeah, I want to simplify this as well. So I want to take this condition, and now you have to remember back to where I said that if you use these sort of block L infinity Lewis weights, then you can then you lower bound the hypergraph energy by this square of Euclidean norm. And if we ignore the linear transformation U, which we can do just by all Euclidean norms are the same, right? So it doesn't really matter. This is just I'm just going to assume U is the identity for simplicity of notation here. Then this norm squared being less than the hypergraph energy, if you think about what that means, it means that the set of vectors of energy at most 1 is contained in the Euclidean unit ball. Okay, and so this comes from the KKTY choice of importance weights, this row vector of probabilities, and it allows us now we're just going to replace this condition by, instead of considering this particular index set T, we'll think about any index set that's contained inside the n-dimensional Euclidean ball. Okay, so now our problem is just going to be to analyze the expected maximum of a random signed sum of squared norms over a set T that's contained in the Euclidean ball. Okay, so here's the general theorem of okay, so this is the main technical result of the paper. That again, I'm going to K here, but this should be going to capital M. So suppose N1 up to N sub capital M are semi-norms on Rn, and that T is a subset of the Euclidean ball. Then the expected, here T might not be compact, so let's replace the maximum by a supremum. Expected supremum over X and T of this random signed sum. So again, this is a sum of norms squared, of semi-norms squared, is bounded by this. Okay, so there's this factor here, which is when you can think about it, this factor has to be on the right. So if this quantity is large, then basically just consider the expected square of this quantity. And so like basically just, if you want to control just the variance of this quantity, then you need to control this thing. It's not the main term. For instance, in the setting of hypergraphs, this is quite easy to bound. one should think about here, the main term is that you get a Euclidean norm, sort of the Euclidean norm of these norms. So in this is like the L2 sum. This is the norm that's the L2 sum of these semi-norms times some factor that depends on the geometry of these norms. Okay, and so there's two numbers here, kappa and lambda. Kappa is the expected maximum norm of an n-dimensional Gaussian, where I say the expected maximum is over these semi-norms. And again, this should be a capital M here. And lambda is the maximum expectation of these things. And this is so bad that I'm going to fix the notation here so that it's not so bad. So if you just, I think the screen sharing is probably turned off for a moment. I'm not doing anything sinister. I'm just fixing the notation. And I'm going to come back. Let's share again. And I think we're back now. Okay, so now these indexes are fixed. So kappa here is the expected maximum norm of an n-dimensional Gaussian, and lambda is the maximum expected norm. Okay, so in general, we expect like lambda would be much smaller than kappa. And in fact, I mean, you see that, you know, like this trade-off occurs here. I mean, lambda has a square root log n factor on it, whereas kappa doesn't. Okay, so this is the main theorem of the paper. And then the special case of hypergraphs is just given by this special case of the theorem. Suppose that there's a linear transformation on our n, mapping vectors into n-dimensional vectors to m-dimensional vectors, and each of our norms is an L infinity norm on a subset of the vertices. And suppose that the maximum size of any of those subsets is R. Then this bound on the right here, relatively easy to compute it, and you just get something like this. So you get square root log m times log R times this quantity, and then times the 2 to infinity norm of A, which is just the maximum 2 norm of any row of A. And in the hypergraph setting, basically, if you remember that we had these alpha e's that were these edge weights, and the sum of the alpha e's squared was equal to n, and that actually makes this here equal to square root of n in the setting of hypergraphs. So like the fact that this is well controlled depends on an appropriate choice of well, both an appropriate linear transformation, you know, to put the space into a nice position, and then an appropriate choice of sampling weights. But with that, you know, with all that in place, one gets this bound. And now if there was this symmetrization reduction at the beginning, if you go through that reduction, then essentially the number of edges in your sparsifier is going to be basically this eventual sparsifier is the square of this quantity. So in this case, you know, I said that this is square root of n. So when you square this, you're going to get n times log of m. But in the hypergraph case, this little m here is n choose 2. It just maps it maps the vector x into the vector of pairs xu minus xv. So that's good. So this is going to give us just n times log n, and then from this r, we're going to get another log r factor. Okay. So now the whole game is to prove a theorem like this, and like I said before, using the generic chaining theory. Because I've gone to a new slide, these indices have gotten bad again. Like they were good at some point though, so just remember them as they were and not as they are now in this slide. Okay, but now for the rest of the talk, we're gonna focus on this theorem. Okay, we have a sub-Gaussian process with respect to some distance d, and I want to bound expected sup of Vx over x in t. So the Fernique-Talleyrand theory of majorizing measures / generic chaining says that there's an entire family of upper bounds, basically one that comes from every suitable hierarchical partitioning of the index set t, and the best possible partitioning is described by this gamma 2 functional of Talleyrand. So it has a complicated definition that we don't need to go into. It is okay, so it's both complicated and not very complicated. I mean, it's not very complicated in the sense that this is the definition of it. So, you know, you just consider all sequences of partitions of this set T such that the piece indexed by H, the partition indexed by H has at most 2 to the H pieces. And then you consider take the best such family of partitions, and then the cost of that partition is the sup over all x and t of this weighted sum of the diameters, where ah of x is the set of the partition ah that contains x. Okay, so it's some kind of multi-scale approximation of the metric space, and then this gamma 2 is a notion of the size of such an approximation, and the best approximation gives you an upper bound on this expected maximum. Okay, and that's just because this is a hierarchical approximation, and what each level of that hierarchical approximation ends up corresponding to is a union bound over the set of vectors in every level. And if every union bound is successful over every level, then you get a bound on the entire thing. So this inequality just represents a bunch of different applications of the union bound, and if you apply it in the best possible way, you get the best possible upper bound here. I should mention that if this process was not a sub-Gaussian process, but was actually legitimately a Gaussian process, which means that this family of random variables, if these were jointly normal random variables, then Talleyrand's majorizing measures theorem says that actually not only is this an upper bound, but these two quantities are within a constant factor. So in fact, this is the only way to prove upper bounds on this quantity, as long as you're okay losing the constant factor. Okay, that's for Nick Talleyrand. This doesn't tell us very much because it's not so easy to see how to take some abstract index set t with a distance and construct a nice partition. Fortunately, an earlier bound of Dudley, which I'm just restating here in the chaining language, says that we can get an upper bound on this gamma 2 just by controlling these entropy numbers. So EH of t here is just the smallest radius r, such that you can cover the space t by 2 to the h balls of radius r. Okay, so it's some kind of covering number of the space t. And if you can bound these covering numbers, and then you take this weighted sum, it bounds gamma 2, which bounds this expected maximum. And just to indicate how this sort of family of inequalities gives you bounds on sparsifying hypergraphs. Again, this is assuming that we've already chosen our sampling weights based on this KKTY block L infinity Lewis weights in the interpretation we gave. Assuming you do that, and now you do this symmetrization reduction, then just this classical Dudley entropy bound already is enough to tell you that you can do hypergraph sparsification down to n log n cubed edges. Okay, so like this is actually already, I believe, state of the art. Just applying the Dudley entropy bound. You can go further. Okay, so like there's two ways you can go further here. One way is that the place where the Dudley entropy bound is not tight is that it's basically using this very homogeneous bound for the space, right? It's for every scale, you just look at how many balls for every number of balls, you look at how small a radius do I need to cover the space by that many balls, or how large a radius do I need to cover it by that many balls. And this is like a uniform quantity for over the entire space. Whereas what you can imagine is that maybe some regions of the space are easier to cover at some scales than others, but then when you zoom in a little further, they become harder to cover, or when you zoom out more, they're harder to cover. And then what this family of partitions does is it allows you to adapt to the local geometry of the space. So like this bound here is tight for homogeneous spaces. In fact, it's tight in the setting of Gaussian processes. There's a family of processes called stationary processes. And then for those processes, this Dudley bound is tight. Okay, so there's two ways that you can improve this bound. One is by constructing a non-uniform chaining in this way. So that's one way. And the other way is actually that is by using properties like convexity properties of the index set T. So here's a beautiful theorem that Talleyrand proved. It's in his book Upper and Lower Bounds for Stochastic Processes. I believe the title is something like that. And it's that if T is the Euclidean unit ball, and your distance d is not necessarily the Euclidean norm, but some distance induced by a norm on Rn, then you actually get an improvement to Dudley's entropy bound. And the improvement here is that you replace basically the L1 sum of these terms by the L2 sum of these terms. And in general, what this will allow you to do is to shave off a square root log n factor. Because what will often happen here is in this sum, there's only log n important terms, and they're going to be all about the same weight. And then in this sum, you're going to have the same log n important terms, all about the same weight. But because you're taking a square root here, you're only going to get a square root log n for the number of important terms versus a log n. So this lets you save a square root log n factor. And indeed, if you apply this theorem, okay, so to get to the setting of applying this with Euclidean unit ball, you do have to do a short reduction. I do it in the paper, but it's a half-page reduction. And then applying this theorem, you get sparsification down to n log n squared over epsilon squared edges, hyper edges. So like, even stronger bound, as I said, you shave off a log n. Okay, let me remind you what the theorem I claimed replaces one of these log n's by a log of the rank. Right, so it's which is nice because in the constant rank case, this gives you n log n. Now we know that for rank 2, for graphs, there are linear size spectral sparsifiers, right? Batson, Spielman, Srivastava. However, those are not proved by random sampling. Any technique based on IID random sampling is gonna lose this log n factor. That's just a coupon collecting problem. So you're gonna have to pay this log n. So at least for like this bound, for random sampling based approaches is tight for every fixed R. Okay, fine. So like this is the boundary proof. How do we prove it? Well, okay, this is the point at which things get difficult and technical. So Rudelson proved a concentration theorem for sums of independent, like for random sums of rank 1 matrices. He proved that because he was considering sort of he was studying some problems about putting convex sets into isotropic position. Rudelson's concentration theorem was used by Spielman and Srivastava to get order n log n size spectral sparsifiers. Essentially, by you can look at the process of randomly sampling edges of the Laplacian as a process of sparsifying the Laplacian, where every edge is a rank 1 matrix. So it is about concentrations of sums of independent rank 1 matrices. In his initial approach, Rudelson constructed explicitly a majorizing measure. So, well, not in fact, that's true what I said. Then Talleyrand saw Rudelson's original approach and suggested that it could be done using Talleyrand's theory of growth functionals. This is the approach that I pursue in the paper here. Rudelson then published that paper as a tech report. He was a postdoc at Berkeley at the time, so he as a tech report at Berkeley. But by the time that paper made it to publication, it was noted by one of the referees that actually the bounds Rudelson had proved were dominated by known matrix concentration bounds. Then I'm now I'll say the name of the bounds in a moment. I'm blanking on the name of those bounds for a second, but let's ignore that. And so in that paper, you will find oh yeah, sorry. The bounds are they're called non-commutative Khinchin inequalities, and in the paper you'll find, in the published version of the paper, you'll find the proof with non-commutative Khinchin inequalities. Nevertheless, the proof based on growth functionals exists as a tech report, and also is expounded upon in I think the last chapter of Talleyrand's book on generic chaining. So upper and lower bounds on stochastic processes. The last chapter is about applications to Banach space theory, and Talleyrand espouses sort of his perspective on Rudelson's construction of majorizing measures there. In order to prove this theorem, one really has to dig into it. It's really a kind of amazing construction. It's beautiful. It uses things like approximate convexity of balls in the metric D. It uses two uniform convexity in a strong way, even though, now I'm going to come back here all the way to this chaining theorem, even though even though in proving this theorem, one doesn't, these norms have no uniform convexity. So uniform convexity is a notion of convexity. It's stronger than convexity, which says that things are kind of strictly convex quantitatively, and quantitatively and uniformly for the entire norm. These norms don't contain any such properties, and in fact, if they were L infinity norms, which they are in the hypergraph setting, then they don't have any convexity properties. Nevertheless, the thing that comes up, which is this L2 sum of the norms, is sort of like, the L2 norm is too uniformly convex. And so in some sense, this sum, the outer sum, is too uniformly convex, whereas the inner components of the sum have no uniform convexity guarantees. Okay, and so one has to be quite delicate in the proof of using uniform convexity of the outer sum at the right points, and then using geometry of the inner norms, which is where these kappa and lambdas come from, at the correct points. It's the construction of real Sonnenthal is really gorgeous, and it was a lot of fun to try and adapt it to get something here. I'm not going to say more about it now. I'm just going to conclude with some open questions. First open question, perhaps the most natural one: can you get rid of this log r? We don't know of any lower bounds or reasons to suggest that you can't. And it is unclear what the answer is. I don't have a great guess. So it's a good question, because I actually don't know on which side of it I fall. Either one could be true. What you should note, I guess, is that if you could get rid of this log r, then you could essentially sparsify not just hypergraphs and not just these restrictions of L infinity norms to subset of the coordinates, but you can embed every norm into L infinity of exponential dimension. So like, basically every norm can be written as some L infinity norm. So if you could actually get rid of this dependence on essentially the dimension of the L infinity norm, then you would show that you could sparsify any L2 sum of norms. Can you do that? Okay, well, that's the second open question here. Suppose that instead of looking at sums of these restrictions of L infinity norms squared, which is the hypergraph energy, you just look at a general sum of squares of seminorms in Rn and ask, can you sparsify that down to a near linear number of terms? So in this paper with Gian Bolapati, Yang Liu, and Aaron Sidford, we showed you can do this if you consider L1 sums of the norm, so just regular sums. And for L2 sums, we don't get near linear, but we do get something non-trivial. So the trivial bound, if you just are a little bit careful, is n squared, and we give n to the 3/2. So like these two questions are very closely related, and in my opinion, yeah, the main open question of this line of work based on the empirical method would be, can you remove this log r, and in some sense equivalently, can you do near linear sparsification for arbitrary sums of squares of norms, not just those coming from hypergraph energies. And like I said, for arbitrary sums of squares of seminorms, you can do something non-trivial, but it's not near linear. And then the last question, which is very natural, is, so like I said, in the case of graphs, one can do better than the empirical method using sort of an optimization-based approach. So for instance, Alan Zhu and Lorenzo Orecchia have this beautiful view of the Batson-Spielmann-Srivastava proof argument as regularized gradient descent with a regularizer defined on the positive semi-definite cone. And here, the geometry of the PSD cone seems essential. And so, but it's not clear if it is. And so, a third pressing open question here would be whether there are BSS style iterative optimization-based arguments that can do sparsification in the setting of more general norms. So BSS is in the setting of semi-norms that are just one-dimensional. So They're just basically like linear, like, yeah, they're just one-dimensional semi-norms. And suppose you go beyond one-dimensional, even to two-dimensional, I believe that we don't know the answer there. So I believe that even for sums of squares of two-dimensional norms, you can ask the question of, can you get near linear sparsification? And we're not near linear. We know you can do near linear. This bound gives you, okay, we know that you can do near linear. What's that? Okay, this bound does give you near linear if you, in that case, using this infinity embedding that I suggested before. The question is, can you do order n over epsilon squared? Can you get rid of the log n factor for anything beyond the PSD cone? The most natural thing to look at is just sums of squares of norms on pairs of, on planes, sums of squares of two-dimensional norms. Can one do anything like BSS in that setting? Just super fascinating open question. And that brings me to the end of the talk. I would love to ask if anyone has questions, but there's no one here. So I'll stop there. And oh yeah, feel free to email me. Yeah, send me an email if you have questions. Happy to answer them. All right, let's end this.